So in this video, I talk about what it means for a function to be continuous, and I bring up one of the big four theorems of calculus, which is the intermediate value theorem. So we'll use the idea of the graph is connected in order to motivate our idea of continuity. So we like to think that if a graph is connected, that it's kind of like a piece of string that has no breaks in it whatsoever. Let's see what that means then if we take such a graph and we look at where the graph would cross the vertical line x equals c. Well, if the line crosses the graph, there must be a point on the graph. So the function has to therefore be defined at that value. So f of c must be some number. At the same time though, since that the graph isn't broken, that means the limit must be approaching somewhere. And finally, if the graph truly is unbroken, where the function is going, the limit, and where the function is, the evaluation, the point, they have to be the same point in the plane. So that then leads to the definition of continuity at a value. We say that a function is continuous on some kind of point in the interior of its domain if the limit of the function as x approaches c is the same as the function evaluated at c. In other words, continuity for us means to evaluate limits, you plug in the number. But it's a lot more than that. This is just the simple algebraic way of expressing it. There are many definitions that are connected to the phrase continuous. So we'll try to go through those pretty quickly. We'll say that a function is continuous at a real number c if and only if the limit of the function as x approaches c is the function value at c. We can also get that the function is right continuous at c or continuous from the right, or left continuous at c or continuous from the left, if and only if the limit from the right or the left is the same as evaluation. Essentially, we're only worrying about numbers to the right or the left and not the entire full limit. Continuing with our normal definitions of continuity, we'll say that a function is continuous on an open interval if and only if f is continuous at every number in that interval. We'll say that a function is continuous on a closed interval if and only if the function is continuous on the interior from a to b, and then also it's got to be right continuous at a, that way we stay inside the interval, and left continuous at b, that way we stay inside the interval. I can't insist on full continuity at a because if the function is defined on a closed interval, the function may not be defined to the left of a or to the right of b, so I can't use the entire limit. We'll say that a function is continuous, just continuous, if and only if f is actually continuous for every single real number in its domain. Take into account that if the domain is a closed interval or a half closed interval, that we restrict ourselves to continuity from the left and the right to stay within the domain of the function. If you look at the function f of x equals x squared, you would notice that its graph has no breaks in it. But then that would then mean that the function is continuous. So you would say that the function f of x equals x squared is continuous. But the logic there is backwards. It's actually, since the function is continuous, then the graph has no breaks in it. Now, if you look at the square root function, it also has no breaks in it. So for that reason, you can say that the function is continuous. But that's because it's continuous on its domain. Sometimes we want to be a little bit more precise and we'll say it's continuous on this. So in this case, you would say that the function is continuous on the interval from 0 to infinity, including 0. Let's try some quick true-false questions to see if you understand what this concept is about. I'm going to ask you a couple of questions about continuity. All you got to do is say true or false. Now, I'm not going to hear you. So what I'll do is I will pause a second and then I will tell you the answer. It's up to you to go pause it if you want to guess. So you ready? Let's start. So then for this graph, is this function continuous at 1? No, it's not. If you draw the line x equals 1, the graph does not have a limit there. So then you have to have the limit in order to have continuity. So no. So the next one. Is the function continuous at 3? No, it's not. For the exact same reason, actually. If you draw the line x equals 3, this function does not have a limit there. Again, is the function continuous at 4? Yes, actually it is. If you draw the line x equals 4, you'll notice that the limit exists, the function value exists because there's a dot there, and the two things agree. Now the next one's tricky. Is the function continuous at 3/2? Yes, it is actually. If you draw the line x equals 3/2, you'll notice that the function has a limit and there's a function value. I just didn't put a filled in dot there, that's all. So you don't have to have that to have continuity. You just can't have a break in the graph. And at x equals 3/2, there's no break in the graph. All right, let's give it another go. I'm going to ask you a question, and then you are going to answer. Once again, I won't hear you, so then I'll pause a second. You can pause me if you want to think about it, and then after that small pause, I will go and give you the answer. Ready? Let's start. So then, is this function continuous from the right at 1? Nope, it's not. If you draw the line x equals 1 to the direct right of it, the graph is certainly connected, and it's going to a point. It's going to that open circle at the point 1, 0. But that's not where the function is defined. It's actually defined higher. So from the right, the graph is considered to be broken. So is the function continuous from the left at 1? Yeah, actually it is. It is continuous from the left, because if you draw the line x equals 1 and come from the left of that line, it's going to a point, and that is actually where the function is evaluated, because that's where the filled in dot is. So yeah, it's continuous there. Let's try it again. So is the function continuous on the open interval from 1 to 2? Yes, actually it is, because since we're using the open interval, we don't consider what happens on the lines. We consider what happens between them. So imagine the vertical lines, x equals 1, x equals 2, and notice that between them, the graph is connected. It doesn't matter what happens at 1 and 2 because they're not part of the interval. Let's try one more time. So is the function continuous from 2 to 3? Yeah. Actually, it is. Yeah, from 2 to 3 because you're not actually looking at. You're not looking at 2 and you're not looking at 3. You're looking between them. So if you take those two lines, x equals 2, x equals 3, and look only at the graph between those two pieces, yeah, the graph has no breaks. So the graph is continuous in that interval. So let's consider the definition of continuity at a number, c, a little more closely. For a function to be continuous at c, the function must have a limit as x approaches c, so that's going to be a number. The function has to have a value at c, and those two numbers must be the same thing. We call this the test for continuity. We just check all 3 steps. So as an example, what if I wanted to show you the function 5x plus 2 is continuous at 1? Well, that's because in order to find the limit of the function, that's just the limit of the polynomial, we can use the limit laws, we get 7. But if we evaluate the function at 1, we get 7. And notice that they're the same thing. So that means that this function is indeed continuous at 1. It's continuous at a lot more than that. But the continuity test only ever works for a single number. If I want to show continuity on a whole interval, I need some more powerful things. So now that we have an idea of what continuity is, at least graphically, it means the graph is not broken. We need to have some way to talk about where the graph is broken. So that would be where it's not continuous. We call that a discontinuity. So by definition, a function is a discontinuous at c, or has a discontinuity at c, if and only if the function is just not continuous. So one of those 3 steps is not true. Either the limit doesn't exist, the function isn't defined, or the limit and the value are not the same. We call the discontinuity, though, removable if the limit does exist. We call it non-removable otherwise. Removable discontinuities are really actually not that bad in calculus. We don't really care very often. Non-removable discontinuities are the ones that you can see very obviously in a graph. If a function has a discontinuity that's in its domain, then we call the function discontinuous. Be very careful. Continuous functions, which means that it's continuous on its domain, can have a discontinuity because it can have a discontinuity if something's not in its domain. So I'm going to give you 3 fairly common examples of discontinuities at a single number. These functions actually are continuous in lots of other places. It's just discontinuous at one or a couple places. And in each case, I'll tell you if the discontinuity is removable or non-removable. So here, this function is discontinuous at 0 because there's a break at the graph when you look at the line x equals 0. But it's considered removable because if you take the limit of that function as x approaches 0, that limit exists. It would actually be 0. In this example, you have a discontinuity in the graph where x is 1 because the function is not defined at 1. If it's not defined, you instantly have a discontinuity there. It doesn't matter if there's a limit or not. But here, if you take the limit of this function as x approaches 1, the limit does exist. The limit's actually 2. So that's called a removable discontinuity. Now, what's so special about removable discontinuities? In these 2 cases, if you were to type these into a calculator and have the calculator graph it, you would not see the hole. You would not see a break in the graph at all because your calculator just can't handle that. So removable means that usually it's something that you could remove by just moving one single point. Or in the case of a calculator, that's not detectable. On the other hand, the floor function, if you were to go and look at any integer, -1, 0, 1, 2, 10, this function would be discontinuous there. This function has an infinite number of discontinuities. Because at each of them, at any integer, the limit wouldn't exist there. This would be called a non-removable discontinuity. If you ever type that function into your calculator and try graphing it, at every integer, something bad's going to happen. Like, it would look like the graph would have a straight vertical line that would connect the 2 points. And you know for a function, you can't have a vertical line. Now, a common technique that we use in mathematics is to take a big problem and to break it into lots of smaller problems and then somehow to zip it back together. We did that with limits, if you recall. Well, but continuity is defined in terms of limits. So because we have limit laws, you should expect like continuity laws. So we'll start with the basic things. These functions are all continuous on their domain. So if you want, you can just say they're continuous. So you might wonder why. At least the first 4 are obvious because they come right from limit laws. Take the sine function. Remember the limit of the sine of x as x approaches c is just the sine of c. And that's exactly the definition of continuity at c. So the sine is continuous at every single number. Notice though that I never actually before this talked about limits of the natural log or the exponential function. And the reason is they're actually really hard to understand why they are the way they are. But we have to start somewhere. So I'm just going to give you that those functions are continuous. And we'll worry about later why it's so. At some point in the course, we'll have to backtrack. Okay, so now that we have some base functions that we know are continuous, in this case on their domain, if we have 2 functions that are continuous at a single number, then the following are also all continuous. If you add or subtract continuous functions, it's continuous. If you take a constant multiple for any constant at all of a continuous function, it's continuous at that value c. If you take a product of continuous functions, it's continuous. If you take an integer positive power of a continuous function, it's still continuous at that number. Continuing with our results, again, assume we have functions that are continuous at a certain number, then the following are then going to also be continuous at that number. The quotient is continuous, provided that the denominator is not 0 when you plug in c, because the function has to be defined or it can't be continuous at all. The nth root of the function is continuous, provided that it exists in an interval about that value, or you restrict yourself to continuity from the right and the left so that it stays in the side of the domain of the function. If a function is continuous and it's invertible, then the inverse is also continuous, but now not at c anymore, but at f inverse of c because you're using the inverse function. Similarly, if you have 2 functions and they're continuous, the composition is also continuous, provided that the function on the inside is defined, that g of c is a value, and that the function f is continuous at that value. So let's do a couple of examples to show you what I mean. We're going to use those continuity laws to take a function and show you why it must be continuous on its domain. You're going to find that practically everything you ever learned is continuous on its domain. So as my first example, notice that x is a continuous function. So then x squared is, because one of the rules. But we also know that x is continuous, so then 3 times x by one of the rules is continuous. Then if I add those continuous functions, that's continuous. But the function 5 is also continuous, so then the difference in those continuous functions is also continuous. So this function is continuous everywhere. Let's try it again. If you look at, say, this rational function, now x is continuous, so 2 times x is continuous, 5 is continuous, so the sum of 2x plus 5 is continuous, x is continuous, so x squared is continuous, 1 is continuous, so x squared minus 1 is continuous, so the division is continuous by the quotient rule, but for the quotient rule, you have to make sure that the denominator is not 0. So then you can't say it's continuous at any value where you would result in a division by 0. Of course, because continuity requires that you're able to evaluate the function. So here you could say that the function is continuous everywhere but 1 or -1. But the way we've defined continuity for functions is that it's continuous on its domain, and 1 and -1 are not in the domain, so you can just say that this function is continuous. Try it again. If you look at, in general, polynomials in any rational function, they're just continuous because they're continuous on their domain. Now, if you were to look at the square root of x minus 2, x is continuous, 2 is continuous, the difference is continuous, and by the root property, it's continuous too. The resulting function is also continuous, provided that you stay within the domain of the function. And here, the domain of the function is 2 and up, so this function is continuous the whole time. It's just continuous from 2 and up. Or if you want, you can say it's just continuous, period. As another example, if you look at the tangent function, it's the division of sine and cosine, which are continuous everywhere. So as long as you don't divide by 0 for some choice of input, then the tangent's defined and the function is continuous. So you might notice, if you remember, the tangent had discontinuities, weird breaks in the graph at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. That was all where the cosine was 0. If you look at that function, it's actually continuous always. It doesn't matter what value you pick because it's continuous on its domain, and in this case, its domain is everything. If you look at this function, the square root of x squared, which we know simplifies to be the absolute value of x, the square root function is continuous, x squared is continuous, and the composition of continuous functions is also still continuous. So the absolute value function is continuous. You might notice that practically everything you've ever learned was continuous as long as you were inside the domain. That explains how you were taught how to graph. You were taught to graph by plotting a bunch of points and then connecting them, right? And the only times you didn't connect them is because they said, look at this 1x value. Something bad happens here. Let's explain what. What you were doing back then in pre-calc was finding the discontinuities and figuring out what should happen around that discontinuity. So you might notice that because of the continuity laws, if you start with continuous functions and only use the typical operations that you use with functions, then the result is continuous, provided that you stay within the domain of the new function. So for this function, the h of x equals x squared minus 16 over x times x minus 4, I might want to know where is it discontinuous. Well, pretty much just look outside its domain. That function then is automatically discontinuous where x is 0 and where x is 4. I could then come back, if you want to, and find out the limit of the function at these values, if it exists or if it doesn't exist, to classify the type of discontinuity. So if I want to look at the limit of this function as x approaches 4 of the function h, that'd be x squared minus 16 all over x times x minus 4. And that would then be the limit as x approaches 4 of x minus 4 times x plus 4, and that's all over x times x minus 4. Since x is not 4, these two factors are common factors and non-zero, so I can cancel them, giving me the limit as x approaches 4 of x plus 4 over x, and that would be 8 over 4, which is 2. So the limit exists. So x equals 4 is a discontinuity, but it's removable. X equals 0 is a discontinuity, but it's definitely non-removable. The function does not have a limit there. For the function g of x, it's discontinuous anywhere. If you remember, secant is really 1 over cosine of 2x. So if the cosine of 2x happened to be 0, then the secant would not be defined. Now the cosine would equal 0 if the angle 2x would be pi over 2, or 3 pi over 2, or 5 pi over 2, or negative pi over 2. And in fact, if you take pi over 2 and add any multiple of pi, where that multiple is an integer multiple, then the cosine would be 0. So x then, if x is pi over 4 plus any integer multiple of pi over 2, then the cosine of 2x would be 0, and the secant of 2x then would not be defined. This function is discontinuous at all those numbers, but it's continuous everywhere else. In fact, the only time that the continuity laws kind of fail us is when the function is piecewise, because a piecewise defined function is not described algebraically by any of the rules that we know. So here, I'd like to know, where is this function continuous? To do this, I'm going to break it into cases. So case number 1, what if x was less than 2? Well, in that case, the function is defined by just a polynomial. And if you pick any value in that interval where x is less than 2, then the limit of that function as x approaches that value, where c would be less than 2, that would be the same as just f of c. That's because if you looked at the interval, this is the entire real line, and here is 2. If this was c, then there would be some interval around that c that within that interval, the function is always defined the same way. It's always defined as f of x is equal to 3x minus 1. So within that interval, the function is certainly continuous. So it's continuous, therefore it's c. Doing at same thing at 2. For case 2, what if I picked a number c that was actually more than 2? Well, if it's more than 2, again, look at the number line. Here would be 2. Here is c. There would be some open interval around c so that all those numbers would be bigger than 2. And for that interval of numbers, the function then would always be defined the same way. It would just be 8 minus x. And that function is continuous because 8 is continuous and x is continuous, so the difference is continuous. So it's continuous for all the numbers in that open interval. It obviously, therefore, is continuous at c. So just the way the function is defined, pretty much these things are instantly continuous for more than 2 and less than 2. What goes wrong is at 2. Because, see, at 2, if you think about the number line, here is 2, and to the right and to the left, you get different function rules. So you can't use the rules that we have for continuity to build small things into large things. So the only way to do this, therefore, is do the test for continuity. So let's do that. So I will do the test for continuity at x equals 2. Or c equals 2 if you want to write that. C equals 2. So then that would then be, I need to know what's the limit of the function. To find the limit of the function, though, since the function changes definition to the right and the left, I'll have to do the right and left hand limits. So the limit of this function as x approaches 2 from the right, if x approaches 2 from the right, it means that x is more than 2. And in that case, the function is always defined as 8 minus x. That's the limit of a polynomial. We can then just plug in 2. And now you know why? Because polynomials are continuous. So then you can just plug in the value anytime you need the limit. So that's just 6. If you take the limit of this function as x approaches 2 from the left, that would then be the limit as x approaches 2 from the left of 3x minus 1. That's now a limit of a polynomial. So we know those are continuous. You can just plug in the number. And that would be 5. Oh no. That means then that the limit of this function as x approaches 2 does not exist. It failed pretty much like the first, or one of the biggest rules we have. If the limit doesn't exist, of course the function can't be continuous there. And since the limit doesn't exist, we have what's called a non-removable discontinuity. If you try graphing that function and look at the line x equals 2, you'd see a very obvious break. But the question was, where is it continuous? So this time you cannot say the function is continuous because it's not continuous on its domain. Now you must state the intervals. So I would say f is continuous on the open interval that's below 2 union the open interval above 2, but not at 2 itself. Here's another variation on the exact same problem you just saw. I want to know if the function is continuous, then what should a equal? Well, notice that, as you saw before, here at the domain breaks, if x is more than 5, it's a polynomial, so it's automatically continuous. If it's less than 5, it's a polynomial, so it's automatically continuous. It doesn't matter what a is. But at 5, the function changes. So at 5, what we have to have, if it's going to be continuous, is that the limit of this function as x approaches 5 must be f of 5. Now, if that's true, 3 things must be equal to each other. First, the limit to the right and the limit to the left both must exist, and they must be the same value, or the limit doesn't exist. So we have that the limit of this function as x approaches 5 from the right must equal something. The limit of this function as x approaches 5 from the left must equal something. And f of 5 itself must equal something. These all must exist and equal each other. All I'm going to do is choose 2 of them so that they both give me some kind of equations that depend upon a, and then I'll just solve that equation for a. In particular, notice that the limit of the function as x approaches 5 from the right is the same as the limit as x approaches 5 from the right of a minus 2x. And that's just a polynomial in x. So I can just evaluate that at 5 to get a minus 10. At the same time, though, f of 5 is defined by a times 5 plus 3, which is the same as saying 5a plus 3. Well, if the function is continuous, it's got to be continuous at 5 because that's in the domain. That means these 2 things must equal each other. So now we know that 5a plus 3 would have to equal a minus 10. That means 4a would then equal negative 13. A must be negative 13/4, and that's the only choice that would work if this function is going to be continuous. So there's a useful continuity interpretation. Another way to think about it, just using hand waving or putting things in layman terms, if you say the limit of the function as x approaches c is f of c, that means that f is continuous at c. Well, limits though say that you can control the output by limiting or restricting the input. But you know what the limit is, and it happens to be the function value. So putting those things together, it says that if you want a desired, that means you have an idea, a goal in mind, if you have a desired small change in the output away from the function value of f of c, then there is a way to get a sufficiently small change in x from c to do it. If you want to say it fast, it's not really quite right, but gets the idea across. A small change in output only ever requires a small change in input if the function is continuous at that c. Now, you've used this constantly. anytime you ever said this is about that, it's actually using continuity. For example, I want to know what's the square root of 4.01. Well, everyone says that's about the square root of 4. That's 2. So it's about 2. What you did is you took the square root function, the square root of x, and you know it's continuous at 4.01. So you just changed the input a little bit from 4.01 to 4, and you assume that the value, the output, shouldn't change that much. That's using continuity. But what we can't do, though, unfortunately, is that if you give me a small change in input, continuity says there should be a small, it's a relative term, small change in output, but you can't predict the small change of input, how it will affect the small change in output. So the output change might be great. You don't actually know. You just assume that for small changes of input, you'll get small changes of output. So continuity is mentioned in a lot of theorems in calculus. So I'm going to introduce you to one of them now. To do so, consider solving the equation you see here. Now, you might ask, well, how to go about doing it. That's not the point. The question is there an answer? So to figure that out, assign a function f of x to the left-hand side of that equation. That then gives you a function of x, which we could then graph. Focus only on the interval from 0 to 3. Notice how the graph crosses the x-axis. When it does so, you get an x-intercept. For that x-intercept, there's an x value and the y value. For that x value, the function is 0. Therefore, that x value is a solution to the equation. So clearly we have a solution to this particular equation. Or do we? Just gotta be careful, because we have seen before where the function will not actually cross a certain line. There's a hole in the graph there. And if this was a removable discontinuity, you wouldn't see it. It would not show up on your calculator. So we have to be careful. Well, but we know that this function is a polynomial, so it's continuous everywhere. So it can't hop over that line. But we need some way to say that nicely. So we have the intermediate value theorem. If a function is continuous on a closed interval, and k is any number between the evaluations of f of a and f of b, then there is a input c between a and b, so that f of c is that value that you desire. As an example, notice that if you were to pick this x value, you would get that point. If I call this a, then f of a is certainly negative. If I were to pick this x value, b, that would correspond to this point in the graph, and clearly f of b is positive. So by this theorem, there is a c between a and b, and in fact, it looks like I can see it. It's right there. That's what c would be. So that f of c is a value that I have between these two things, which in this case is 0. So there has to be some c, so f of c is 0. And that guarantees that there is a solution to this equation. Now, the theorem, though, doesn't say how to find it. It just says that it exists. That, though, just knowing that it exists is really powerful. This particular theorem is actually one of the big 4 theorems that separates calculus from pre-calculus. So as a fun interpretation of the intermediate value theorem, this is called the pie cutter game. So then we're going to take a pie, and we're going to cut it in half. You get your share, and I get my share, and we'll hopefully have the same share. So here, oh boy, that's the pie. So here I go, I'm going to cut it, and I get above and you get below. So clearly that wouldn't be fair. So I'm going to take that cut that you just saw. I'm not going to change the direction it's in. I'm going to raise it and lower it only. And can you visually see where to put that line if you just raise it or lower it so that it would split the pie exactly in half? The question you should ask yourself, though, is, can it be done? Well, yeah, I just have to think about the whole problem in terms of the intermediate value theorem. So here is an axis system to help us talk about things. I'll move that line up and down just by its y coordinate. So as that line goes up and down, there would be a defined area that's below the line, and there's a defined area above the line, and those two functions should change continuously as h varies, because small changes of h give you small changes in these outputs. Seems like it's continuous. So if you were to define the function f of h to be the difference between them, notice that this function is positive sometimes and negative others. So if I pick an h value, so the line's way below than the curve, for that particular h value, which I'll call a, then f of a would wind up being a, well, that would then be a negative value, right? Negative value, because everything now is above the line, and you'd be subtracting that positive value, and this would be 0 because there's nothing below it. On the other hand, there is certainly a line way up here that has a y-intercept of, let's say, b, so that f of b would actually be positive, because now everything is below the line, and this would be all the area, and this would be 0, as there's nothing below it. So notice that for this function, some of the times it's positive, sometimes it's negative, but we know, or at least we're assuming, that the two area functions are continuous. So their difference is continuous. So f is continuous. We have that f is continuous on the interval from a to b. So by the intermediate value theorem, there is a choice of height, which I'll call c, so that f of c is 0. That means that the area below the line would have to equal the area above the line. So there is a way to do it. And if I just sort of guess it, it looks like it's about there. Now, you may not believe me, but that's okay, as this is not a pie that either of us are going to eat anyway. And that gives you a basic introduction to continuity and the intermediate value theorem there at the end. You won't use the intermediate value theorem that often, but you actually do use it a lot in life already. You just don't realize you're doing it.